All right. Thanks, Sebastian. Today, my name is Andrew Chu. Now, today I'll be presenting my paper, Understanding Privacy and Quality Trade-offs in Synthetic Network Data. This is a joint work between our group at the University of Chicago and Cal Poly University. So the setting of this talk is about computer network data, and it's a very important piece of data. Researchers, academics, companies, they use observations about all the network data and their streams of information to improve their systems and build new systems. You can take it as an example, Netflix. Maybe they're aggregating all of the telemetry data from their video streams, and they're using that to determine where to place a new CDN server to improve video quality experience for their users. If you're Cloudflare, maybe you're observing trends in anomalies to try to figure out a new heuristic to prevent denial of service, right? And in the ideal world, there's probably multiple objectives that different organizations could share. And if you could share all this data, it'd be really helpful to try to just understand the landscape of the internet. But in reality, that's not the case, right? People are concerned about their customers' data or getting leaked or the internals of their own network being exposed. And so one way people have thought about getting around this is by generating synthetic computer network data. The paper that's up here is one of the first papers to propose this. And the idea here is that if you train some model or just have some technique to produce synthetic data on the ground truth, you'll get similar distributions as the ground truth, but it's not the real data. And further, you can also add privacy enhancing technologies to really try to make sure that there's no leakage, right? These are good efforts, but unfortunately, it's the case that they're not really robustly evaluated with respect to privacy. So a lot of the times in these papers, they'll just kind of slot in something like DP and crank up the epsilon, or I guess lower the epsilon all the way down to something very high privacy budget, like 40 or something, which doesn't really give you anything useful. So there's a gap there actually measuring how much privacy leakage there is to begin with, and if DP actually helps, right? So in this presentation, I'm trying to answer these two research questions. For one, how vulnerable are these generators to privacy leakage? We evaluate this through membership inference attacks. And the second one is, how is the quality of synthetic data affected when you add DP? And we measure this through fidelity and utility, which I'll get into later. So just for some background, there's mainly two different types of synthetic network data generators. There's traffic attribute generators, which take as input and output summary statistics about a network. And there's two main methods, machine learning-based ones that are generative, and also probabilistic methods. There's also raw packet generators, which take as input and output raw packet captures, so PCAP files, and they will actually generate very granular packet level, like PCAPs you can dissect with Wireshark or something. And the methods for these are all generative. In this work, we evaluate these four different generators. Full disclosure, one of my works is actually I attack my own work here, so I have the NetSSM model. But all the results in this presentation will be focused on these four generators. So just some more background on MIAs. The idea here is you try to leverage models' tendencies to memorize qualities of the training data, and an adversary will use this to try to determine if there's some target record that exists in a trading data set. DP's been covered by previous two speakers a lot, but the idea is you add some sort of calibrated noise, and in the machine learning training setting here, that'll help prevent model overfitting, and in turn that can maybe protect against membership inference attacks. Right? Okay, so for the first research question, the way we approach this is we train a number of all of those different models I showed under two different paradigms. So it'll be under the non-DP case and the DP case. And we conduct membership inference attacks against all of them. So the adversary has these following capabilities. Largely, it's a white box. So they have access to the underlying distribution of training data. They can generate their own records and query the model, see the output, see the intermediate states. And their goal here is to try to determine if there's a specific network trace that was used to train a model. So kind of tantamount to like an individual. Here, our granularity is a network trace. To do this, we use two different data sets that are broadly categorized into 6 different classes. And we partition each class into 50-50 splits. And then we train all of these models on these splits for both DP and non-DP paradigms. Our membership intro attack is a binary classifier-based membership intro attack that uses the shadow training method. And what that comprises is, first, we build these shadow data sets from the 50-50 splits. One of the splits we hold out to kind of act as the actual ground truth training data set for some target model that an adversary might want to attack. In the second split, we randomly sample it to build 10 shadow training and validation data sets. The trained data sets would act as kind of candidate member samples, and the validation as non-member samples. In total, we train 1,000 different shadow models across the different classes, models we're evaluating, and the privacy budgets. And then using those shadow models, we build attack model trained data sets by feeding back in those member, non-member samples, and then tagging each of the, extracting the last layer embeddings, logits, prediction vectors, whatever, and tagging them as being member or non-member from their corresponding shadow data set. And then we use these data sets to train attack models and evaluate those attack models on that first split that was supposed to be like the ground truth target model training data set. So we find that in the non-DP case, both this NetShare model and NetSSM model are vulnerable to membership inference. But for NetDiffusion, get some interesting numbers. We can, I think it's best to explain this visually. So these are actual training data samples for NetDiffusion and from 3 different classes. You can see at the very top, there's maybe this band of color that's a little bit different of how the data is encoded. But in general, images look almost the same, right? And if you compare this with some other common image data sets, it's a lot different. If you have like an MNIST data set of handwriting, different numbers will be the same number, but they're still different. Same for the other ones. I don't know, planes or clocks will be different, but still planes or clocks. Here, different classes, different, and even in the same class, everything, there's kind of a same pattern. So what ends up happening is that NetDiffusion undergeneralizes here. And so it learns this majority signal that's present across everything. And then when you try to conduct membership inference attacks against it, it can't, everything looks the same to it, right? When we add DP to all these models, we find that in NetSSM, this makes the MI ineffective, and I'll explain why in a bit. NetDiffusion remains ineffective because you're adding noise just to something already noisy or that doesn't contain a signal. And surprisingly for NetShare, it remains effective. We chalk this up to something called mode collapse that occurs in the GAN architecture, which basically is very strong structural overfitting. So there's the model will try to always predict low variance values that are consistent across all of these samples. And because you're regressing towards some continuous value, even when we add noise to try to address this, it can't resolve this mode collapse. NetSSM, you have standard overfitting with the cross entropy loss, which DP is able to help with. NetDiffusion, like we said, is undergeneralized. Getting into the quality findings about the data, so fidelity and utility, we measure fidelity with distributional distance metrics, and utility, we train different downstream classifiers and regressors to see how useful DP data can be. For fidelity, this is the distance between the synthetic DP data and the ground truth. We see that across a bunch of models. There's actually not that large of a distance, which is interesting. But NetSSM, which is token-based cross-entropy model, which could explain some of that, there's a large distance. So our takeaway here is that DP doesn't necessarily lead to low fidelity synthetic network traffic, and that this can be dependent on the generator. For utility, we train 2 different types of downstream models for classification and regression. And for the classification case, we can see here that, again, for like similar to fidelity, the performance varies across generator. But it's also interesting, as we can see with like NetSSM, even though we have low fidelity with NetSSM, it doesn't necessarily mean that the utility, when you feed it into some downstream model, is negatively affected, right? So kind of a give and a take, I guess you could say. For regression, it's also similarly a little bit interesting. You can see on the far left, you have this bar for no DP models trained without any DP. And in all of the privacy budgets that we evaluate and all of the models, you can see there's actually some model that performs better than the non-DP case. And we do some more evaluation in the paper, but basically find that sometimes DP can actually act as a data regularizer and can help improve the performance of the attack models because it doesn't overfit to patterns that it sees in its trained data set. Yeah. So overall, I think the takeaways as well here are that DP as itself is very proven, but the effect on these network traffic generators varies based on the architecture and the training objective and stuff like that. And practitioners and people should think carefully about how they apply DP instead of just kind of applying it blindly and thinking it'll solve everything. So thank you, everyone.